Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized conversations.
Today, we're talking about a really cool approach to AI alignment. That's the challenge of making sure AIs do what we actually want them to do and do it safely.
Right, because telling an AI to make people happy could go wrong in a lot of unexpected ways. This paper, AI Alignment via Incentives and Correction, takes a page from a very human field, law and economics.
Exactly. Think about how we align humans in society. We don't just hope everyone is nice. We create systems of incentives. For example, the theory of the rational offender from the 1960s says that a person deciding whether to break a law weighs the potential gain against the odds of getting caught and the severity of the punishment.
So it's a cost-benefit analysis. A bigger fine or a higher chance of being caught makes the crime less profitable. This paper argues we should think about AI the same way.
Precisely. Imagine an AI model, let's call it the solver, whose job is to answer questions or write code. Sometimes the easiest thing for the solver to do is to just make up an answer. This is what we call a hallucination. It might look persuasive, but it's wrong. In this model, that's the crime.
And the gain for the AI is that it was faster or it used less energy, or maybe it just produced an answer that it predicted would get a good score even if it wasn't true. So how do we stop it?
You hire a cop. The paper introduces a second AI called the auditor. The auditor's only job is to check the solver's work. If the auditor catches a mistake, the solver gets a punishment, which in AI training means its internal settings, its weights are adjusted so it's less likely to make that mistake again.
Okay, that seems straightforward. One AI does the work, another one double-checks it. Problem solved.
But here's the brilliant twist in the paper. The auditor AI is also a rational agent. It's also learning from incentives. And what's the auditor's incentive? Well, checking work costs time and computational power.
I see where this is going. If the solver AI gets really good because the punishments are so effective, it stops making mistakes.
And if the solver never makes mistakes, what does the auditor learn? It learns that spending its energy to check the solver's work is a waste of time. It never finds anything, so the auditor gets lazy.
That's a huge problem. The system looks perfectly safe because the solver is behaving, but actually, the police have gone home. The oversight has vanished. If a new, tricky problem comes along that the solver gets wrong, no one will be there to catch it.
That's what the paper calls the fixed point problem. Stronger penalties can deter the solver, but those same penalties can accidentally destroy the auditor's incentive to keep checking. It's a delicate balancing act.
So how do you solve that? How do you keep the auditor motivated even when the solver seems perfect?
You change the game. This is where mechanism design comes in. Instead of just rewarding or punishing the final outcome, was the answer right or wrong, you reward the entire interaction. You create a much richer feedback signal.
What does that look like in practice?
Well, you assign different values to all possible scenarios. For instance, if the solver gives a correct answer and the auditor correctly identifies it as correct, that's the best outcome, high score.
Makes sense.
If the solver makes a mistake but the auditor catches it, that's also a good outcome. Not as good as getting it right the first time, but it shows the safety system is working, so the auditor gets a reward for a successful catch.
Okay, so you're incentivizing good police work.
Exactly. But then you have the bad outcomes. If the solver makes a mistake and the auditor misses it, a silent failure, that's a huge penalty. That's the worst case scenario. And if the solver is right, but the auditor incorrectly flags it as wrong, a false positive, that's also penalized because you don't want an overzealous auditor.
This is a much smarter reward system. It's not just about the solver, it's about the health of the whole two-agent team. So did they test this out?
They did, with a really cool experiment. They had a solver AI whose job was to write Python code, and the auditor AI's job was to look at that code and try to find a bug.
And crucially, they didn't just pick one set of rewards and stick with it. They had a higher-level controller that was constantly tweaking the rewards, like a manager trying out different bonus structures to see what works best.
This is the adaptive reward part of the paper. This manager, which is a smart algorithm, tries out different reward profiles. Maybe it tries making the penalty for a silent failure even bigger, or it gives a bigger bonus for catching a tough bug. It watches to see which reward profile leads to the best overall behavior from the solver-auditor team.
And what happened? Did this dynamic game theory approach actually work better?
It worked brilliantly. Compared to other methods with fixed static rewards, their system reduced the solver's hallucination rate, that's the rate of incorrect code attempts, by 32%.
Wow, that's a huge reduction.
And what's more, the solver AI learned to be more careful. It learned that if it wasn't sure about the answer, it was better to just abstain, to say, I don't know, rather than guess and risk making a mistake.
That is such an important skill for an AI. We want AIs that know their limits.
And they also showed their initial fear was justified. In one of their comparison models using a static reward system, the auditor AI did exactly what they predicted. It eventually collapsed into doing nothing because the solver got good enough that it wasn't worth the effort to check.
So the key takeaway is that when we're building safe AI systems, especially ones where AIs are monitoring other AIs, we can't just set it and forget it. We have to think like a game designer.
That's the perfect way to put it. AI alignment isn't just about training one AI to be good. It's about designing a robust system where all the parts, all the AIs, are continuously incentivized to work together towards the goal we care about, which is a safe and reliable outcome. You have to reward the oversight, not just the performance.
A fascinating paper that shows keeping AI on the right track might mean we need to be clever economists as much as we are computer scientists.
Thanks for tuning in to Daily Papers. We'll be back next time with another deep dive into the world of research.